Okay, so this is joint work with Umur Dakar, Artur Shagarov, Adrian Guato, and Philip Tchaikovsky. So what I'm going to talk about is our efforts to make it easier to write fork-join parallel programs in a high-level style and in a way that allows them to execute efficiently on real hardware. So a fork-join program is just a parallel program that where it's easy to exploit opportunities that you can find in divide and conquer parallelism. There's a lot of languages that provide native support for fork-join programming, including X10, Java, and Silk. The one that we'll be using as the example in this talk is Silk. This slide here is showing this sort of running example for the talk. It's taking as input a loop range and a function, and it's applying the function to all the iterates in the range. So you'll notice that the way that the function expresses parallelism is by the spawn sync keywords. So spawn corresponds to a fork point and sync to a join point. So basically these are hints to the system that there's an opportunity for parallelism, and it's up to the system to decide whether or not to realize the opportunity. Okay, so right. So in order to realize an opportunity for parallelism, I'm going to define this fiber, which is an object that can realize a fork point and actually move the parallelism in the fork point across cores, so actually realize parallelism. Okay, so every fiber has a cost, and that cost individually, cost for creating the fiber, and that cost might individually be small, but taken as a whole could become quite large. So if it's large enough, and this happens quite often, it could be large enough to totally negate the advantage of parallelism. So clearly what we'd like to do is be able to say, to have some guarantee that we can bound these fiber creation costs for any fork join program, and that's what the work that we've done here is addressing. Okay, so if you want to do that, you have really two options. Either you can try to reduce the cost of creating an individual fiber, or you can try to reduce the number of fibers that you're creating. So there's been a lot of work in various systems on reducing the cost of creating a fiber, but unfortunately this isn't sufficient for really fine-grained parallelism because these overheads can add up, and in particular they do for fine-grained programs. So what people do in response then is they use one of these two approaches. So one of which is granularity control. So in granularity control, what you're trying to do is predict the run-in time of a computation so that you can ensure that a given fiber contains enough work to amortize its cost. So this approach works sometimes, but it's challenging because it requires annotations in the source code, tuning in order to do good prediction, and also it applies only to certain classes of fork join programs. Alternatively, you can try lazy scheduling, where the idea is to try to move the critical fiber creation overheads as much as possible to the last minute when you know that it's likely that you want to move that fiber to a different core. So this approach works well for a lot of programs, but it isn't really backed by any formal guarantees, and actually there are known adversary cases where it breaks down. So the technique that I'm going to be presenting on is basically a runtime technique that applies to any fork join program. It has bounded costs on fiber creation, and it has a guarantee on achieving good CPU utilization, and it has an implementation that's competitive with state-of-the-art systems. So fork join is a concept that dates back to the 60s, but a lot of the work on language support dates back to Halstead's multi-Lisp system in the 80s, and then continuing up to now. So the big picture is you have programs like this map program here that compile down to some parallel binary where you have computation graphs that kind of express the available parallelism in some way. So I'll be using computation graphs in the sense that like every vertice corresponds to a step in the execution of a fiber, and every edge corresponds to a controller data dependency. So then you have a runtime system then that maps the parallelism in those computation graphs onto the actual cores. So every time the program enters in a fork point, the runtime has to make a decision between one of these three alternatives. It could either immediately create the fiber, or it could sequentialize the computation, basically ignoring the spawn sync keywords. Or it could keep around some data so that later on it can try to create the fiber from the bookkeeping data. And that's where this approach where our approach kind of falls. So as I alluded to earlier, there's been a lot of work on reducing overheads for fiber creation. And even so, it's still common to see programs like this kind of modified version of our map function here, where what you're doing is throttling the number of spawn syncs your program is passing through by using this grain parameter. So the problem is that this grain parameter is highly dependent on the context surrounding the software. So there's a lot of reasons why this doesn't work, and they're kind of summarized really well by Tzanis et al. But basically, it's a problem because the goodness of the grain depends on the software context and the execution context, including details of the architecture, number of cores, and so on. So the idea of heartbeat scheduling is basically to amortize the cost of creating a fiber against past work. So at runtime, each core tracks how long it's been since the last time it's created a fiber. When enough time has passed, the core wakes up and checks the call stack of the currently running fiber. If it finds some latent parallelism in the call stack, then the core will liberate that parallelism. So to implement this system, you need basically an alarm clock that's waking up on a regular basis. I'll go into some detail on how we implemented that, but on the machines we experimented with, typically a good range is an alarm going off every 20 to 50 microseconds. Fortunately, it's easy to find a good setting for a given machine, and you can find it quickly by a simple tuning process, and it's just once per machine. So now let's just consider what happens when a heartbeat occurs. Okay, and we're going to use this map function as the example, and we're going to follow the execution of the call to the main function. Now, notice that main is calling map on the range 0-4, and we're stopping, the heartbeat is stopping the program right at the core, that is right at the point that it's at the second call to map on the range 0-2. So that's what our call stack looks like. And then at this point, what heartbeat does is it looks at the call stack and finds that there is indeed a latent opportunity for parallelism in there. and it's corresponding to the upper half of that range of 0, 4. So what it does at this point is liberate that parallelism into a new fiber. And then there's just that's almost it. There's just a couple other steps. So the next thing it does is create a join point for these two new parallel computations, and then registers the dependency edge so that it executes properly. And at that point, heartbeat, the promotion stops, and heartbeat, and the program continues running. So so now I'm going to talk about the formal bounds that we proved for heartbeat scheduling. So to prove the bounds, we used the work span model for fork join, the work span cost model for fork join. So in the model, the work corresponds to the total number of computational steps, and the span to the length of the critical path through the computation graph. Okay, so so one kind of classic result in this space is the bound on work stealing scheduler. So work stealing is a load balancing algorithm. It's basically handling the step that the problem that occurs after you've created the fiber, and it's basically handling how the fibers get balanced between the cores. So this bound is upper bounding the execution time of a program on P cores to doubly the work over the number of cores plus big O of the span. Now, the bound is in expectation because work stealing is a randomized algorithm. And there are two kind of important points here. First, it's bounding kind of the critical costs of load balancing, and that's basically orthogonal to the granularity control problem, but it's still nevertheless an important component. The second thing is that it tells us when to expect linear speed up, and that's the case when that first term there dominates. Okay, so to account for, but I should say that the one thing the work stealing bound doesn't account for, of course, is the fiber creation costs, or the granularity control. To do that, we introduced a few parameters. There's tau, which accounts for the cost of creating a fiber. This is easy to infer, in fact, on a given machine, on a given language implementation, given machine. And there's also h, which is the heartbeat duration. We typically pick h to be a factor k of tau. We'll see why that is in a second. So this is showing the work stealing bound, including the costs of fiber creation. There's two new terms. The first one is saying that the total cost of fiber creation is bounded to 1 over k fraction of the total work being performed by the computation. So if we pick k to be 20, then basically we're ensuring this is guaranteeing that the total cost you're paying for fiber creation is 5% of the total work you're doing. But to get that guarantee, you have to pay in reducing parallelism somewhat. So that second term there is saying that you're getting a bounded increase in the span in proportion to the amount that you're saving on the fiber creation. Okay, so we to test this idea, we implemented a prototype in C++. For the prototype, we used work stealing to do the load balancing. We had to implement promotion. We had to change the calling convention. So what we ended up doing is taking every function in the program and encoding it as in a class-based representation. And really the main point there is that to implement the heartbeat, we instrumented the function calls and the loops with checks, and each check would read from the cycle counter to test how long it's been since the previous heartbeat. So this approach is the software polling approach. Alternatively, you can have an interrupt-based approach, but it turned out to be simpler for our prototyping to go with software polling. So the calling convention had to change, like I was alluding to. One change that we implemented that's totally standard for fork join is we used a cactus stack data structure to represent the call stack. But we extended that data structure with a doubly linked list that's basically connecting all of the frames that contain some latent parallelism in them. The reason we did that is that we needed a mechanism so that when promotion kicks in, it can, in constant time, access the oldest opportunity. It can find the oldest piece of latent parallelism in the call stack. There's one other point that I don't have enough time to really go into detail on, but it's that we also found it important to implement native support for parallel loops. The short version is that it's too expensive to introduce a new frame for every parallel loop, so we had to build a mechanism into the system to access that parallelism on the fly. And that mechanism was inspired by the lazy scheduling implementation. So this plot here is showing the main experimental results. These benchmarks are benchmarks we took from the problem-based benchmark suite, which is a collection of C++ of kind of idiomatic Silk codes that were written by other researchers. These benchmarks represent a variety of workloads, and they're kind of designed to test irregular parallelism. So it's a particularly challenging case for granularity control. Now, we took as baseline the original author's Silk codes and ran these experiments on a machine with 40 cores. So you're seeing here basically that overall we perform better. Usually, in a few cases we're a bit slower. The paper kind of details why that's the case in particular cases, and it's either because one system is generating more fibers than the other, or is better utilizing the cores than the other. So the other result here that isn't showing in the plot, though, is that the original author's Silk code used 3 different kinds of manual granularity control techniques, a variety of heuristics, and these showed up in various places all across the code. What we were able to do with this implementation was use a single uniform technique and none of those manual techniques, and in many cases get better results. So there's been a lot of related work over the years, and the first kind of category here is work that tries to establish formal bounds for fork join. Heartbeat is, this work here is kind of the first to include in that category granularity control with end-to-end bounds. The second category are approaches that try to tame scheduling overheads. Heartbeat is sort of the first in this class to have both end-to-end bounds and in a state-of-the-art implementation. There's also prediction-based methods, one of which is Oracle-guided scheduling. This method has end-to-end bounds, but they don't apply to all fork join programs, just a certain subclass, whereas Heartbeat applies to all of them, and it comes with an implementation that applies to all fork join programs. So in conclusion, heartbeat scheduling is the first technique to provide end-to-end time bounds for accounting for scheduling overheads. It basically allows you to simplify your code and at the same time, in many cases, achieve better performance. Thanks.
We have time for a few questions.
Thanks. I mean, this is a very ambitious area, and it's very clear from the related work that it has been a difficult problem. I'd like to understand better how you account for the cost of the cactus stacks, because intuitively it sounds difficult to have any bounds on this kind of data structures because of the heap management overhead, essentially.
So the cactus stack data structure we use this kind of stacklet-based approach where you allocate a 4K chunk for like kind of a region of the cactus stack. So the data structure does kind of fit within the bounds because we do have some stack ripping going on, as you can kind of see in that example, but that operation is constant time.
There's no log tree or something to...
No, in fact, it's all
completely
constant time.
bounded.
It's a bit subtle, but in fact, the way that we use a cactus stack is not really any different, except for the doubly linked list than other systems.
Okay. And another question. So you didn't account for synchronization costs at all. So where does this go? Like you only count the fiber creation, not the actual sync.
That's a good point. So you're thinking in terms of, you could also think of synchronization in terms of the scheduling queue.
Yes.
Although in the work stealing case, you don't really have that. But yes. So indeed, we assume that this tau parameter is a fixed cost. So it's really just
talking. Everything.
Yeah, it's a fixed cost for that machine. So it's really just accounting for the kind of the overhead cost.
The total runtime. Okay.
Yeah.
Okay. Thanks.
Other questions? If not, I have one. So in my work long ago now on this sort of task stealing and such, one of the key questions was in your concurrency, when you're doing a fork and join, is the concurrency elective or mandatory, in the sense that if I fork two tasks, can one of them wait on the other in some sense? Which then can I force the system to have to do concurrency? Does your system?
No. Yeah,
which
so
way do you go?
that's a great question. So yeah, so indeed we assume that doesn't happen. So if you wanted to go, I would sort of call that going to like futures, so something like equivalent to futures, and where you have like an explicit kind of blocking operation. And actually the bounds would not apply in that case, because what can happen is you can accumulate latent parallelism in the stack. You may or may not have enough credits to release any of it right now, then you block, and now you have to think differently about what it's doing.
So concurrency is elective, that is,
Yes.
Its fork means do it if you want to, but semantically you don't have to.
Yeah.
Okay. Okay, do we have any other questions? If not, let's thank the speaker again.